Hello, everyone. Come on in. I'm sorry for the delay. Something happened. I'm trying to get in there. Come on in, everybody. Come on. All right. Looks like we got Agnes in here. So, anybody have any questions before we get started? Again, I apologize. I came in, it looks like 3 minutes late. I apologize for that. I had some difficulties. Anyways, it's taken care of, and we got to jump into more or less chapter 23 and then finish that up with one problem and then jump into 24. So, capacitance and dielectrics and stuff. So, anyone have any questions? Got 9 of you in here now. That's looking a little better. All right. So one thing I need to do is I need to work an example. Not unlike what we did last time. We did do some examples. If I remember correctly, I think I did a loop. Hold on a second. I think I did a loop of wire. So I had like a uniform charge per unit length on a wire that was shaped in the shape of a circle, and I calculated the electric potential above that. And then in principle, you can take a derivative of that. The negative gradient of the voltage, in fact, gives you Z. Actually, I'm looking at my notes now, and it seems like I didn't. No, I ended up not doing that with your class. Okay, so we got a couple more problems to work. No big deal. We did work a voltage problem for a dielectric, so that's good to see. Let's get cracking on what to do with this. This is 242, which I need there. And another person come in. That's good. We're getting there. So today is the 3rd. So I'm going to make 10-03-2023. That's our new one. And that's what the data file is going to be called. And that's what the video is going to be called. So I just want to make sure everybody knew what that was. Of course, you can always go to Google Docs to get the document. That's the reason why I tell you that. And of course, that's also one of the search things you can use on my YouTube channel to find that specific video. So let me go ahead. Looks like we got 10 students in here. Let me go ahead and share my screen because we got to work a little bit more of the problems from the chapter on voltage, which I seem to recall was 23. So now I'm going to click share screen on my side. Looks like it's working. That should pop up for you guys any second now. Looks like it's still going. I'm going to go ahead and start drawing a coordinate system. And actually, before I do that, I think I'm going to go ahead and draw the hoop, if you will. So I can make that my hoop. And that be the inner part of my hoop. And now I can draw a coordinate axis there, coordinate axis there, and a coordinate axis there. That's my z-axis. This is my x-axis, and this is my y-axis. I'm going to say this has a radius of r. And what I want to know is what is the electric field at this point, 0, 0, z. And actually, sorry about that. I shouldn't be calling it E at this point. So let me change that and say V. at P is the question mark. So that's what we're looking for, the electric potential at question mark. I will tell you the solution goes like this. We do, or I should say, the charge is uniformly distributed. So that means Q total is equal to lambda times DL, say, and that'll be some differential length specifically around the loop that I'm going to use. Okay. The solution part that we need is dV is equal to dQ over, and actually I should have said a D in front of that Q over there, over 4 pi epsilon naught, just plain R like that. Now, the description of this equation, of this calculus related equation, is that the voltage can be obtained by integrating dV, which is also equal to dQ over 4 pi epsilon naught R. And you're going to integrate that such that dQ is a differential charge element and R is the distance from the location of the specific dQ you're looking at to the position at which you wish to know the electric potential. So that's what the R is. And dV is a scalar, so you don't have to be much more complicated than that. Now, what I'm going to do is I'm going to go ahead and show you how we'll figure out exactly what the dQ is. So if you imagine allowing the angle that you know from polar coordinates, say, if you allow that angle theta, or if you actually allow a line to go from the positive x-axis counterclockwise towards the positive y-axis out an angle theta, then that'll mark the beginning of a differential line element. The beginning of that differential line element, whose length is going to be dl, which I'm going to work out in a second. And the way I actually define it is that dl starts at angle theta and then ends at angle theta plus d theta. So this angle right here is d theta. And of course, you can see that the radius of the hoop is the length of those little orange lines, or excuse me, little red lines. So dl must in fact be equal to r times the change in the angle, which is d theta. Does that make sense to everyone? Is that a reasonable line element to use? So that means that dq is equal to lambda dl, which equals lambda r d theta. So now I can go ahead and compute v. V equals the integral of dv, which I'm going to go ahead and pull out the 4 pi epsilon naught in front. So I'll say 1 over 4 pi epsilon naught integral. Now I'm going to substitute my dq, which is lambda r d theta, and I still have the distance from the differential line element to the point z. I think you can see that those red lines have a length capital R, and then from the origin up to the point P, that distance is z, and the distance that we're looking for from DL to z is the diagonal that goes from r theta up to z. So all we got to do is take the square root of r squared plus z squared. Like that. Does everybody agree with that assessment? Does that all make sense anyways? I'm not, when we do stuff like this, it's not that we expected you to come up with it on your own. If you did, that's great. But we expect you to, having seen it, be able to do that again. to problems somewhat like that are exactly like that. Okay. This one actually had a uniformly distributed charge. And since it's uniformly distributed, you know the total charge, you could call it Q. So we could say, for instance, Q total is equal to lambda times 2 pi r. And that tells you that lambda is equal to Q total over 2 pi r. So that's how we could actually interpret what lambda is, in case you have any confusion of that. But that should basically be the formula. Now what I can do is notice the integration is going to take place with theta, and I'm going to integrate from theta equals, actually I should probably write that in blue. I'm going to integrate from theta equals 0 to 2 pi. And what you're going to get, of course, is notice the lambda and r come out in front. The 4 pi epsilon naught stays out in front. But you're also going to have an r squared plus z squared under square root. That's in the bottom, but also out front. And we get the integral of d theta from 0 to 2 pi, which is obviously going to give me lambda times 2 pi r over 4 pi epsilon naught square root r squared plus z squared. And of course, you could also interpret this. This will be v at 0, 0, z. Okay. We could also interpret this to be Q total, in case, in this case, it seems I just gave you lambda, but I could have worded it such that I gave you lambda and Q, or I could have worded it where I gave you lambda and then I'm guessing at what Q would be, or I could give you it where I suggest I gave you QT, and then you got to figure out what lambda is if you really want to. But I'm allowing for all those bases to be covered. The 2 pi r times lambda is QT, because 2 pi r is the circumference and lambda is the charge per unit length. So now I've got QT over 4 pi epsilon naught square root r squared plus z squared. So that's the ultimate expression for the electric potential. Remember, this would be called voltage, electric potential, stuff like that. Now, it turns out that what we've stumbled upon is something very big and important mathematically. And basically, there's this string of facts that if one of them's true, then all of them are automatically true. And I'm going to give you those now, and then I'm going to use one of the results. So condition 1. E is a conservative vector field. And when I say the word conservative, I mean in terms of there happens to be a conservation of energy or something like that associated with that force. So that's what we mean by the phrase conservative. Now, sometimes people will write 1 and 2 as if it's one thing, and that's fine too. I'm just trying, because I haven't necessarily had you guys for 241, though some of you I did. I'm trying to explain to you what this conservative part means. So what the conservative part means is that the curl of E, which is defined to be del cross E, which is really the determinant of, I'm actually doing a lot of definitions here, more so than I'm writing the theorem, but that's mainly because I want to make sure everybody's on the same page. But what you would do, at least in rectilinear coordinates, is you use I hat, J hat, and K hat for the first row. The second row would be the partial derivative with respect to x, which I'm just going to write that way for using less space, the partial derivative with respect to y, and the partial derivative with respect to z. And then the third row has to be the x component of E, the y component of E, and the z component of E. And this is identically zero. Okay, what identically means is that it's not, when you do this computation for the electric field, say, you'll get this vector. And if each of the individual components of the vector are not automatically zero, then it's not identically zero. If you get it where it has some x's or y's or z's in it, and you have to figure out what x, y, or z makes it zero, that's not identically zero. Identically zero means it comes out to be zero. So that process where I took the del operator, where del, oops, wrong thing, where del you can think of as an operator, which means its intent is to be put next to something. And when you put it next to something, what happens is you take the derivative of the thing that you put next to it with respect to x, you take that derivative and you multiply the answer times I hat. You also take the thing that you write next to it and take the derivative of it with respect to y, and then write that next to j hat. And then you take that thing that's supposed to be next to it and you take the derivative of that with respect to z and put it next to k hat. And then you add those three terms together and out pops a vector. That's what this gradient, this del operator is. So I do know that in Brazil they call it nabla. Don't know why, but that's what they call it. Okay. So, anyways, that's what that little del operator is. And you can take that del and it can act on a scalar function, in which case it's called the gradient, and it converts a scalar into, well, it sort of converts it into what we call a directional derivative, but it's basically a derivative in space. Okay. You can take it and do a dot product of it with a vector field, in which case that's called the divergence. And it tells you how much the electric field appears to be emanating from a specific point. Or you can take that del and do a cross product of it with E, in which case that tells you how a certain field appears to sort of go in concentric circles around a particular spot. So that's why they call it the curl, and that's why they call the other one the divergence. So those two are two of the statements. And remember, what I'm saying is, if you can prove any one of these are true, then all of them are true. And I'm going to be a little wishy-washy on one of the last ones. One, because I haven't looked it up recently, and two, because I want to point it out to you. But I can't give you like all the gory details. One, because I haven't looked it up in a while, but two, because you haven't covered that much, unless you're about 2/3 of the, or let's say at least about 3/8 of the way through differential equations. So number 3, if all of this is true, then here's a cool mathematical symbol. If you write upside down backward E, that means there exists a scalar field V. And if you write that, that sort of looks like a cursive S followed by a cursive T. That's because it means such that. So there exists a scalar field V such that E is equal to the negative gradient of V. So basically what this is saying is, just like we learned in 241, you could do Newton's laws of motion and study all those vectors, but then you got towards, chapters 7, 8 and stuff like that. We started doing conservation of energy, and that was a way where you could avoid a lot of the vectors. You could work with scalar functions. And the reason why that was possible is the gravitational force, either as m times g in the j hat direction, are in the negative j hat direction, or the GMM over r squared in the negative radial r hat direction. Both of those are conservative force fields. And because of that, you get a scalar potential. The scalar potential for the mg version is U is equal to mgh. And the scalar potential for the GMM over r squared is supposed to be GMM over r. But that's all because the E, or in the case of the gravitational force, the force F is conservative. Okay. So this is what's necessary. If you have a conservative field, and that conservative field means that the curl is 0, then there exists a scalar field that you can use to represent the force field, and it allows you to bypass vectors. So for instance, because of this, you have another factor or another fact, and that is the integral from A to B of E dot dl, which I think you recognize is sort of like a work thing. That's just going to equal V of B minus V of A. And it's going to be independent of path chosen. I don't have to put the word chosen there, but I wanted you to understand that remember when you do a line integral, you're supposed to choose a path. A lot of times you can get away by not even realizing it's choosing a path. You're just sort of doing what you've seen other people do, and you'll still get the right answer. And a lot of times that happens, and it might even be the majority of the time it happens. But in reality, sometimes you get in a pickle where you have to do it properly. And when you do it properly, you've got to choose a path, and you've got to choose the direction in which you're going. What this theorem says is that it doesn't matter which path you choose. You can choose the one that's easiest to calculate. And because of this conservative nature of this field, it's going to be the exact same answer no matter what path you choose. And in fact, the answer is going to be the difference in the electric potential, or excuse me, in this case, the difference between the scalar field at the two locations. There's also another one, the closed integral of E dot dl is equal to 0, which I think is pretty much covered by 4, but we always put it as a separate one. You can see that if A and B were the same location, then the potential at A and the potential at B would be 0, it would be the same, and the subtraction of them would make that 0 no matter which way you went. So that's why the closed integral is equal to 0. Now, the last thing, this is the one where I said I'd get a little wishy-washy on, but basically there is a correspondence between these types of fields and stuff of that sort, such that the exact differential equations that you study in differential equations are of this form. So that you could have, for instance, dv is technically the partial derivative of v with respect to x times dx plus the partial derivative of v with respect to y times dy plus the partial derivative of v with respect to z times dz, and that all could be set, for instance, equal to 0. That 0 equal sign and then that 3 terms together basically make a form of a differential equation that if you've had differential equations you've seen before. But what happens is you'll have some neat function like 2x squared plus y, or 2x squared y minus z, or something like that. And you'll have that function times dx, and then you'll have some other entirely different function after a plus sign will be multiplied by dy. And in the differential equations world, what you do is you take the derivative of the one in front of the x, take the derivative of it with respect to y, and then you take the one in front of the dy, take the derivative of it with respect to x. And since the order of the derivatives isn't supposed to matter, meaning if you take the derivative of the x first and then with respect to y, or y first and then with respect to x, that shouldn't matter. If that's because that's the case, if those two derivatives that you took are now equal to each other, then you can say it's an exact differential equation, and there's a very specific process you go through to solve it. So this is all related to that. So I'll just say that I'll put a little asterisk on it just to remind you that I'm giving you a gloss over of what it means. But the main thing is, now that I have that number 3 here, I can use that to find out what the voltage would actually be, or excuse me, what the electric field would actually be at that point P, which is 0, 0, Z. I can figure out what that voltage is by taking the negative gradient of that potential. So that's what I'm actually using. Remember, the way the same thing this works is the way this whole thing right here works is that if one's true, all is true. If one is true, all are. Okay, so now that we have that, I'm going to go ahead and borrow this thing for the next page. Oops, I read the wrong thing. I was trying to lasso. So I'm going to copy that. Now I'm going to go to the next page. And I'm going to say paste that. So now I have exactly what I had before. So what I want to do now is I want to use the fact that E is equal to the negative gradient of V. And what this means is, since this one is only a function of Z, I can say that E sub Z is equal to the negative derivative of V with respect to Z. And that's a partial derivative, of course, which we've talked about in lab to some extent. But anyways, or hopefully you've talked about in lab to some extent. So let's start by doing that. I'm going to take the derivative of V with respect to Z, and I'll take the lambda 2 pi r version. So I'm going to say lambda 2 pi r over 4 pi epsilon naught. And then I'm going to say the derivative with respect to Z of r squared plus Z squared. And that could be written as to the negative 1/2 power. Now, at that point, you can also see that this pi and this pi cancels out, and this 4 and this 2 cancels out, leaving a 2 there. So I'm going to say this is, in fact, lambda r over 2 epsilon naught is the actual constant out in front. Now, the derivative of this, I just used the chain rule. So I'm going to take the derivative of u to the negative 1/2. That's going to give me negative 1/2 times u to the negative 1/2 minus 1. So that'd be negative 3/2. So I'm going to say r squared plus Z squared. And now I do negative 1/2 minus 2/2, which would be negative 3/2. So this is going to become negative 3/2. And now I got to take the derivative of u, which is r squared plus Z squared. So that's just plain 2Z. Okay. So now I've got negative 2 lambda r Z over the 2 in the bottom is going to multiply by the 2 in the bottom already. So that's going to be 4 epsilon naught. And I'm going to have r squared plus Z squared to the 3/2. Of course, that's in the bottom, so I don't have to write the negative anymore. And now I can still make some more cancellations. But before I do that, why not just go ahead and write EZ out instead of just the derivative? So EZ is equal to the negative of the partial of V with respect to Z. Notice I already had a negative sign in there, so that's going to make this positive. And now I've got this 2 again is going to cancel out with this 4, and that's going to leave a 2 there. So I'm basically going to say lambda. Oops, I should probably keep it in black. I'm going to say lambda. Dang it. I did everything but change the color of the font. There you go. Lambda times R times Z over 2 epsilon naught R squared plus Z squared to the 3/2 in the denominator. Okay, so that is actually what the electric field is, at least the Z component of it. So you'd actually write the electric field as E with a vector symbol over it equals this function that we see here with a J hat after it, and you'd be good to go. Now, if you look, there was an example in your book in chapter 21 where we did this exact same thing. So you should compare this. Compare this result for E in chapter 21 done by integrating Coulomb. It's a lot. So in chapter 21, we did a ring of charge just like that. And what I'm telling you is we got this exact same answer, but it was a lot harder because in this one we did have to integrate, but we integrated something quite simple. And then we just had to take a derivative, and a derivative is almost always easier than an integral. And ultimately we got it back. So our integral that we did was way easier than the integral that we did in chapter 21. And then the derivative was a little bit extra work, but still not very hard. So we can see that we got the equivalent. Anybody have any questions on that? All right. So just to recap, what we used was V equals the integral of dV, which is dq over 4 pi epsilon naught r. The dq, remember, is always going to be lambda dl, or sigma times dA, or rho times dV. Okay, and this lambda is a charge per unit length, the sigma is a charge per unit area, and the rho is a charge per unit volume. So, like for instance, the rho would have units of coulombs per cubic meter, sigma would be coulombs per square meter, and lambda would be coulombs per meter. Hopefully that helps a little bit. So you're always going to try to find some sort of source like that. If it's uniformly distributed, that just means that one of those values, lambda, sigma, or rho, are all three in some sense, are constants. And since they're a constant, that means you can take the total charge divided by the total length for the case of lambda, or the total charge divided by the total surface area in the case for sigma, or the total charge divided by the total volume in the case for rho. And you can set that equal to the itty bitty bit of charge that you have divided by the length or area or volume of the itty bitty length that you have. Okay. So that's just something that goes on and on and on, not only in Coulomb's law, but in Gauss's law. And later we're going to do something like it in Ampere's law as well. So we did that. We realized that the distance, the R that's in the denominator, means the distance from the differential piece of charge, the dq, to the point P at which we wish to know the magnetic field. In this case, we see that the differential charge element dq is a distance r in the xy plane away from the origin, and the distance to the point P is a distance z along the z axis away from the origin. Those two directions are perpendicular, so that tells us we got to use the Pythagorean theorem to figure out what the diagonal of that triangle is. So the triangle has basically a length r laying in the xy plane, and then it has a length z sticking out perpendicular to the xy plane, and that diagonal is just the square root of r squared plus z squared. That's why I did that. Luckily, all those things just come out in front of the integral because you're only integrating with respect to theta. So it ends up becoming just the integral of d theta from 0 to 2 pi. Now I can express that in terms of lambda as I did in the middle expression in the red box, or I can express it in terms of the total charge, which I call qt, as I did in the right-hand side of the red box. Anybody have any questions on that? Now, once we did that, we then had a voltage, and we could use that to, and the fact that the gradient, the negative gradient of the voltage will give us the electric field. And I did that to find the electric field. I want to remind you, I use this term right here, and this means there exists. And I use this term right here, and this means such that. Everything else I think is pretty straightforward. I've defined what the determinant is, or I've defined what the curl is, and therefore the cross product as well. You see it's a determinant of a matrix, blah, blah, blah. And then this is how I ultimately did the gradient. Since only the z variable was represented, and this only applies along the z-axis, by the way, then I was able to just take the derivative with respect to z, and that would give me the z component, which, of course, that's the only component as long as we stay along the z-axis. If we get off the z-axis, it's going to have an x and y component as well. But anyways, we just took a derivative. We took a derivative of it with respect to z, multiplied it by -1, and got this answer. And what I'm telling you is this is the same result we got by doing it using Coulomb's law in chapter 21. Okay. No questions? All right. It's okay to feel a little blown away, just like when we first started chapter 21. That's the nature of it. It's a little ugly, but there's a limited number of problems I can assign you. The only things I can do to make these more complicated or different and still you be able to solve them is maybe I put some bones on lambda and say, well, lambda is going to be a constant. And if the total charge Q is 4 microcoulombs and the radius is 3 meters, what would lambda be? Or I could say, what if lambda is equal to some constant times theta? Then I could actually make it something where you're going to have to integrate something with respect to theta as opposed to just d theta. In the case of the infinitely long wire with charge on it that's straight along the z-axis, I could say, let the charge density be some constant times r, or some constant times r squared, or some constant times r cubed. That's the easy way I can change that and have you do the exact same work that I did in the Coulomb's law integral form that we use in chapter 21. I could even say, well, let's not let it be infinitely long. Let's say that in fact it's finitely long, but we're going to allow the wire to only go a distance, let's say 5 meters down, but it's going to go 50 meters up. So just by changing the ranges of integration, you get an entirely different formula, because now I'm not integrating from negative infinity to positive infinity. I'm integrating from -10 to positive 50. So stuff like that can happen. So if you just study these and try to think of ways in which you could change them a little bit to do them differently, then you're ready to go no matter what I throw at you. So just try to rework the ones that you've seen, both the way that I do it as well as the way your book does it. And I really don't care if you do my way or the book's way, as long as you get a way that you understand, that's great. All right, we're going to do another one now. This time we're going to do a circular disc instead of a circular loop. So let me start off by drawing said circular disc. Like that. And that would be great if I'd put it on the auto thing, but I did not. So, okay, that looks pretty good. It's not perfect, but I'm trying to tilt it a little bit because you can see the thing's a little tilted, but I'm just going to ignore the fact that it's tilted, and we're going to pretend like it is perfect. Now that's supposed to be a coordinate axis, and it was supposed to be black. So I'm going to, let's just, if only I knew how to delete. Undo. Okay. All right. Now I'm going to draw it black. So there's going to be my z-axis. Actually, I'm still in the perfect drawing mode, so I don't want to write a letter yet. And there's my x-axis. So now I'll put it in regular mode. There's x. There's y. Whoa, there's y. and this is going to be Z. And again, I'm going to want to know voltage at 0, 0, Z. I'm going to say this thing has a radius of R and a charge, total charge, Q, uniformly distributed. Okay. So it's got a uniformly distributed charge. It's obviously a surface area. So that immediately makes us think dq should be equal to sigma dA. And that's what we're going to do. So now I'm going to draw sort of a differential area element. I'm going to draw a loop of charge like this. And I am going to say that this radius is R. And I'm going to say that this thickness, whoa, this thickness right here is dr, and that this quantity right here is dq is equal to sigma times dA. And I'm going to say that dA is equal to 2 pi r dr. Now, what I'm suggesting is if I cut, say, right along there, right along that x-axis and laid that out, it would actually look something like this. Okay, where this thickness right here is dr, this length is 2 pi r right here, and this length is 2 pi r plus dr, like that. And in fact, you can see if it were truly a rectangle and it stopped right at those little red lines, then the area would be exactly 2 pi r times dr. That's what I said it was. If you look in my YouTube channel, you'll see where I actually explain by calculating what that really is, that the dA only differs from what I use, 2 pi r dr, by terms like dr squared or higher. But if you wanted to see it, it's really just that shape there is actually just pi r plus dr squared minus pi r squared. That's really what's going on there. So if you carry out that squaring of the r plus dr, you'll see that it is the actual area. So really all we're doing is we're ignoring that little bit and that little bit. Actually, it should be right there. That's the difference between this symbol and the dA that we're using. Okay. So now we'll go ahead with our solution. I'm going to say solution. Obviously, dV is equal to dQ over 4 pi epsilon naught r. So I've already told you that dQ, well, I used a big Q, so let me stick with that. dQ is equal to sigma times 2 pi r dr. In fact, I can use this idea that Q is uniformly distributed to say that sigma is essentially equal to Q over pi r squared. So we can use that later if need be, and I will, of course. I can also find out that R is kind of weird to define it this way, but notice there's no part of dq that isn't this distance away. So that's why it's actually reasonable to use it. So R that we're using is in fact going to be, and I'll put it in quotation marks to let you know that I'm talking about that one. It's going to actually be r squared plus z squared square root. So I can now say that v equals the integral of dv, which equals, let's go ahead and pull out the 2 pi sigma and the 4 pi epsilon naught out in front. And what we've got left is RDR on top. And then on the bottom, I have the square root. And I'm actually going to write it in the opposite order. Z squared plus R squared, just because I'm used to having the variable that you're integrating be in the back side, not in the front side of the term. So that's the actual integral we have. You can see that this pi is going to cancel out with this pi, and this 2 is going to cancel out and leave a 2 down here. So I get sigma over 2 epsilon naught. So this is going to become sigma over 2 epsilon naught. And now I'm going to say, I'm going to use a technique of integration called substitution, which I'm sure you all know of. But let's say let u equal z squared plus r squared, then du is equal to 2r dr. So what I need, I've got an RDR up there already, but I need another 2 up there. So if I put a 2 up there, I got to put a 2 out here on the bottom. So I'm going to just take this and slide it in there and write 1/2. And then I'm going to write this as the integral of du. Actually, let me write it another way. It's cleaner. I'm going to say u to the negative 1/2 times du. And I'll leave the range of integration off of it for right now. It's not too big of a deal. When I put the z squared plus r squared back in, then I'll make the range of integration in terms of r. So the integral of u to the negative 1/2 becomes 1 divided by negative 1/2, which is the same thing as multiplied by negative 2. So I'm now going to get sigma over 4 epsilon naught times negative 2. Notice the blue 1/2 I already absorbed down in the bottom and made it 4 instead of 2. So that's taken care of there. And now I'm going to have the u function, which is z squared plus, wrong r, plus r squared. And of course, that's going to be to the negative 1/2 plus 1/2 plus 2/2, which would be positive 1/2. So it's going to be to the 1/2 power. And now I've got to, oh no, that's it. Now I've got to do the range of integration, which is from r equals 0 to big R. So finally, I can say that v is equal to negative sigma over 2 epsilon naught times square root z squared plus r squared minus, now I'm going to set r equal to 0. So I end up taking the square root of z squared, but it's a principal square root. So that technically becomes just the absolute value of z. And I can make this prettier just by getting rid of the negative. And I can get rid of the negative by changing the order of the subtraction. So I'm going to call this sigma over 2 epsilon naught times absolute value of z minus square root of r squared plus z squared. Now the z is really the variable that matters. So I went ahead and put it back in the end, or the last term. And that's what the voltage is. Anybody have any questions about that? Okay. So now we can go ahead and use E equals negative gradient of V to compute the electric field. And in this case, again, we're only in terms of Z because we're along the Z axis. So we can say E sub Z is equal to the negative partial of V with respect to Z. So let's compute the partial of V with respect to Z. Well, the sigma over 2 epsilon naught is going to stay. The derivative of the absolute value of Z, it's basically, if you look at a graph of the absolute value of Z, what you'll see is it's basically a check mark at 45 degrees, hits the origin, and then goes 45 degrees with a negative slope. So really all you get is 1 for the derivative. So this is going to be 1. And then if I take the derivative of z squared or r squared plus z squared to the 1/2, that's going to be, I have the minus already, that's going to be 1/2 r squared plus z squared. And then that's 1/2 minus 2/2, that's negative 1/2. And then times the derivative of r squared plus z squared, which is 2z. And what I get, of course, is that this is equal to sigma over 2 epsilon naught times 1 minus z over the square root r squared plus z squared. Now, E sub z is equal to the negative partial of v with respect to z. So now all I got to do is multiply that by a negative. Again, I'm going to do so by changing the order of subtraction. And you'll see that this result just becomes sigma over 2 epsilon naught times z over the square root of r squared plus z squared minus 1. And that's what the electric field is. And again, I'll ask you to compare this to the answer for a similar problem. I think I just put an extra I in there. Oh well. From chapter 21. Okay, what you'll basically see is, of course, yeah, we got the right formula again. And that's it. We've completed chapter 23. So anybody have any questions on any of that? All right. So we're going to go into chapter 24. And chapter 4 is where we talk about capacitors. So capacitors and dielectrics is chapter 24. Hopefully I'm remembering these numbers right, because I'm using like 5 different books, so I could be remembering the wrong chapter. The main thing is the chapter on capacitors and dielectrics is what we're doing next. So that's capacitors and dielectrics. So I want to start off by explaining that a dielectric is sort of a fancy word for a insulator. And we've already learned that the concept of conduction or insulation is a spectral thing. It's not a either or thing. So things that we call insulators can very quickly become a conductor if the electric fields are high enough. For instance, air, if you get an electric field strength of 3 million volts per meter, then if you have a potential difference between, let's say, a cloud and a lightning rod, and you have an electric potential difference of 3 million there, and the distance between the cloud and the rod is no more than 1 meter, then absolutely lightning will strike. That means air has broken down as an insulator and has become ionized, and as an ion well, I should say like an ion bath or an ion gas or what you call a plasma, basically. It becomes a plasma that actually allows current to flow from the cloud to the ground or vice versa. So that's what I mean by saying an insulator and conductor are not, 100% absolute. What one person considers to be a conductor, another might consider to be an insulator, because that other person might work with extremely high currents. But the main thing is dielectric just means this thing is like a insulator in that current doesn't easily flow through it. Okay. So the idea of a capacitor is really just a mechanism or an object or a thing that you can use to store energy, just like a battery, only it can deliver it really fast. It's almost, well, I say it's almost impossible to kill them. They actually get damaged quite a bit, but they still last longer than batteries. So you can, recharge and uncharge and recharge and discharge and recharge and discharge a capacitor, millions of times probably, whereas a battery, even one's made for recharging, you can't get that many out of. They're going to die eventually. So the capacitor is better in that way, but the capacitor is also better in that it can deliver that energy lightning fast. So it's not only a high energy source, it's a high power source because it can deliver it in such a small period of time. You've encountered them before. In fact, just about every electric motor you run into, for instance, the motor that spins your washing machine basket, the motor that spins your dryer basket, the motor that pushes a golf cart, or the motor that turns the fan in your air conditioner. All of those things are electric motors, and all of them electric motors generally use what they call start capacitors. If you've done the Faraday lab, for instance, you know that you have to give that little device in station 9, you've got to give that a pluck to get it started, and then the little 3-poled magnet will spin on its own, as long as it's got magnets on each side to keep it going and a little bit of current flowing through it. Well, the giving it a pluck is sort of what the start capacitor does. It sort of gives it a pluck, gives it that energy to jump out at first, because electric motors start up slowly, but they can have a lot of power. So you use that for that. What they look like in terms of everyday circuit devices is you'll sometimes see them look like this, which always cracks me up. It looks like they have little pants on. It's like a little dot or something. So that's one picture of a capacitor. It looks like that, and that top could be sort of a reddish or orangish or blue or whatever, and it's sort of puffy. That's why I drew that little spot on it right there. So that's a capacitor. There's a lot of different shapes, though. You also have some that look like this. This is actually a pretty odd one, but you will see them on occasion. It's much more natural for something that lays on its side like this and has a wire sticking out at each end. It's much more natural for that thing to be a resistor instead of a capacitor. But in this case, I'm letting you know specifically such devices exist. Okay, so that's a capacitor. The more usual one you see looks more like this, which looks just like that other one, except it's vertical and the two legs come out of one spot in the bottom. That. So those are all capacitors. That's usually what they look like. A lot of times they'll have up here a nice little Mercedes symbol like that. And what that does is, if this thing actually fails, a lot of times when it fails, it'll get so hot and stuff will build up so high in there that it'll pop along those Mercedes lines and make a crack in that, and those little pieces will actually stand up. So you actually, when you look at it, say as a technician, you would see, oh wow, this cap's been blown. I can see where the metals popped up, something like that. So that actually happens. I've actually been lucky enough to find things that I needed to fix, and I open them up and I see one of the capacitors is like that, and I look out, because all then I got to do is find out what the capacitance and the power and temperature ratings are, because they are designed to be able to withstand certain temperatures, certain powers as well. So you got to look up that kind of stuff. But generally, the thing about capacitance that matters, about capacitors that matters, is the capacitance. So capacitance, that's given the symbol C, and it's really defined to be the amount of charge Q it can hold for a given voltage V. Okay. The units of capacitance you can see from that formula is, of course, coulombs per volt. But that happens to be defined to be the farad, which is paying homage to Michael Faraday. And the more likely results that you'll run into are millifarads, microfarads, picofarads, stuff like that. I will tell you that I think I've seen one capacitor in my life that was a microfarad that actually had the Greek letter micro on it. So a lot of times I see this on it, and that too means microfarad. Hopefully more manufacturers will get on board and start putting micro on there, because I imagine at some point we're going to have to actually use megafarad capacitors, and that would be a problem. I'm not positive that we're going to. A 1 farad capacitor is a ton of capacitance. 1 farad can generate enough spark to kill you. So you know, if you store these kind of things around, it's best that you wire the terminals together. So for safety, you would take a wire, a conductive wire, and wire them together like this. Okay. And that way, atmospheric changes and stuff like that are not going to cause charge to build up over time. And also, if someone happened to have charged it up during some process where they were using it and then didn't completely discharge it, it's not going to be holding that charge. So it would surprisingly slap you with a shock. So yeah, you should wire the terminals together for safety.
Wouldn't that short it out?
Yeah, it does. And there's some danger, of course, when you're doing that. You don't want to just grab a piece of bare wire and do it, because that would be basically summoning the shock to come get you. Okay. But what you normally do is you use a grounded line, and you touch the grounded line to both sides, one at a time, say, and then you can wire them together. If you need a grounded wire, by the way, or a grounded line, remember your light receptacle in your house looks like this. And I never remember which side the big eye's on, but this goes to ground. So you can take your wire, and don't mistakenly put it in the other one. Good Lord, it'll hurt. But you put it in that little half mouth down there at the bottom. And long as it's actually touching metal inside, then it's touching ground. And you can then take the other end of the wire and touch things, and it'll discharge them for you. Do not trust the housing of wires, because the housing is mostly there to prevent corrosion and bad things happening to the metal. And there's no guarantee that any housing is enough to actually prevent you from getting shocked. So you just always assume it's going to shock you if you touch the housing. Does that help you?
Yeah.
All right. So that's the fundamental formula that we use for capacitance, is defined to be the charge per unit voltage. Of course, you can also solve that for Q, and you'd see Q equals C times V. You could also solve it for V, and you'd see V is equal to Q over C. So that's the three ways we use it. I'll also tell you that it stores energy. And for instance, if you know the capacitance and the voltage, the energy stored is 1/2 CV squared, which looks a lot like 1/2 KX squared or 1/2 MV squared, and that's going to become relevant later. You can also use C equals QV, or C equals Q over V, for instance, to make that into Q over 2. So I'm replacing the C with Q over V. So that'll be Q. One of the V's will cancel out. So it's QV over 2, 1/2 QV, I think. Double check. Oh, wrote on something. Yeah, so that would be Q over V times V squared. So that'd be 1/2. Oh, dang it. 1/2 QV. Or you could replace the V with Q over C, in which case you get, this was CV squared, in which case you get Q squared. And this was the one I was getting confused with and trying to force it into that one. So those are the three different forms that you can use. So if it asks you how much energy stored in a capacitor, all you got to ask yourself is, do I know the C and the V? If I do, I'm going to use 1/2 CV squared. Do I know the C and the Q? If you do, use Q squared over 2C. And do I know the Q and the V? If you do, use 1/2 QV. So that's all that's really saying. That comes in really handy. What I need to do now is show you what a simple capacitor is. And the simplest capacitor really is the parallel plate capacitor. So parallel plate capacitor looks like this. Basically, you can imagine one plate and another plate next to each other. The general thing that's going to happen is they will be charged up, so that this one might have a charge of plus Q and have a surface area A. This one's also going to have a surface area A. It'll have a charge of negative Q, and this one will have a wire coming out of it as well, like that. And we might even add that this distance right here is D. When you do that, you can find that the capacitance has a very specific form. So if you recall, we found, all right, let's do it again, actually, just for the heck of it. I'm going to change from green to black. I'm going to draw a coordinate system really quickly, but I'm also going to draw a diagram of a really large plate of charge. Now, here's my coordinate system. Let's say this is going to be X, this is going to be Y, and this is going to be Z, like that. And I'm going to say that this goes off to infinity, and this goes off to infinity, to infinity, to infinity. But what that really means is if I look for a distance Z above, that Z is going to be way smaller than the width of that plate. Way smaller, like at least a factor of 10, but preferably a factor of 100 or larger. So doing that actually is good enough. Now, using Gauss's law, I'm going to try to create a Gaussian surface that should have on all the faces either an electric field that's exactly perpendicular to the face and therefore constant on that whole face, or it's parallel to the face and can be a quite bit different, but it being parallel is going to make it have no flux whatsoever. So what we know about electric fields and Coulomb's law tells us that if I make a plane, a circular plane, that's a distance Z up above the plane, And then I make that sort of like the shape of a soup can. So I let this come down and hit the surface of the charged plate like that. And then it goes a little further down like that. Then that's my Gaussian surface. And I've got a dA top is going to be dA k hat. I've got dA bottom is going to be negative dA k hat. And then I've got dA soup label is equal to basically, let's say some dA times n hat that depends on I hat and j hat, but it's only an xy plane vector. So that's why I put it that way. Okay. So now I can say left-hand side, the closed integral E dot dA. Now I've got to compute that. My hypothesis is that E is equal to positive E of Z k hat for Z greater than 0 and negative E of Z k hat for Z less than 0. So this left-hand side is going to become integral over the top of E of Z k hat dot dA k hat plus integral over the bottom of negative E of Z k hat dotted with negative dA k hat plus the integral over the soup label, which is plus or minus E of Z k hat dotted with dA n hat. Now, dA n hat has to be 0. So we can write this now. I'm going to say equals. I'm going to draw this arrow over here. Okay. So what I'm going to get is E of Z is a constant coming out in front, and I get the integral of dA over the top of k hat dot k hat plus E of Z. Notice the two negatives in this one canceled out. I should write this a little clearer so y'all can see that's bottom. Times the integral over the bottom of dA k hat dot k hat. And then plus, in this case, the E of Z is definitely going to vary. So I have the integral over the soup label of plus or minus E of Z dA, but then I have a k hat dotted with an n hat that only depends on I and j, meaning it's like some number times I hat plus some number times j hat. So clearly, if you take the dot product of those two, you're going to get 0. Whereas you take the dot product of these, you're going to get 1 and 1. So ultimately, the result is 2E of Z times A. Now, the right-hand side of Gauss's law is Q enclosed over epsilon naught, which is equal to sigma A over epsilon naught. So now I can say left-hand side equals right-hand side. Sorry about it getting so small here, but I didn't really want to start on another page where you couldn't see everything. I've now got 2E of Z times A is equal to sigma times A over epsilon naught. You can see that the A's cancel out, and ultimately what you get is E, the vector, is equal to sigma over 2 epsilon naught k hat and negative sigma over 2 epsilon naught k hat. And this is z greater than 0, and this is z less than 0. Ooh, that's supposed to be z less than 0. Okay, so now we have the electric field. All I've got to do, I've got 2 minutes left. So the electric field between the plates, if I write my plate here and write my plate here, actually, let's take this one and make it red. So this is negative Q, and this is positive Q. And I get an electric field between the plates of sigma over 2 epsilon naught due to the positive plate, but I also get a field pointing this way of sigma over 2 epsilon naught due to the negative plate. Out here, I still get that, but I get this as well. Out to the left-hand side, I get this, but I still get this as well. So what I see is E equals 0, E equals 0, and E equals sigma over epsilon naught between the plates. So now I want to use delta V equals VB minus VA equals negative integral E dot DL. And I'm going to do that assuming my drawing is like this. There's my x-axis, there's my y-axis, there's my positive plate, and here's my negative plate. This negative plate is at a distance d, but that corresponds to position A, and this corresponds to position B. So I'm actually integrating from right to left. So this is going to be negative integral. My electric field is going to be sigma over epsilon naught I hat. And then my DL, I'm going to use it to indicate the direction. So I'm going to say negative dx I hat. So that indicates direction. Okay, that means my range of integration has to go from low coordinate to high coordinate, which will be B, which implies x equals 0 to A, or excuse me, to A, which implies x is equal to D. So now I can see that I get negative times negative would be positive sigma over epsilon naught integral dx I hat dot I hat. This quantity, of course, is 1, and this integrates from 0 to d. So ultimately, what I get is equals sigma over epsilon naught times d. Now I'm going to use C is equal to Q over V to get C is equal to, the Q is sigma A, and then the V is sigma over epsilon naught D. So you end up getting epsilon naught A over D is the capacitance. So the capacitance for a parallel plate capacitor is epsilon 0 A over D. And that process I just went through is the single, well, it's one of the two most important paradigms of this whole 242 course is, can you do this sequence where you use either Coulomb's law or Gauss's law to compute the electric field? Then you use that electric field to calculate the voltage from one part of a capacitor to the other. Then you use C equals Q over V to compute the capacitance using those two results. And notice the capacitance comes out in terms of geometry and stuff that's stuffed inside. Like you can put a dielectric constant in front of the epsilon 0 to represent that the stuff between the plates is not air or vacuum, but is a dielectric. So we can do this with all the different types of symmetry. You can do it with a cylindrical capacitor. That would be like coaxial cable, or this was a parallel plate capacitor. You could also do it with a spherical capacitor. And that's it. We've done enough for this. I've gotten through what I wanted to. You guys are free to go. I'm going to ask that or I'm going to stay here till the last person that leaves. But until then, you have me. So feel free to ask me any questions. Thank you for coming, everybody.
Professor,
Mm-hmm. Yes.
do we have any like online tests or anything like coming up?
I'm planning on opening one. I don't think I've done it yet, and I was hoping to do it before class, but I ended up having those problems, so I didn't get to. Let me look real quick just to make sure. I don't think I've done one for yours, but I'm planning on putting one, and it wouldn't be due until like Thursday or something. But let me see what we've got. We've got our practice tests, which we did 1 and 2, which was 17, 18, 19, 20. I'm supposed to do chapter 21 and 22. I think I will open that tonight, and I'm going to make it due probably Thursday of next week. I might, depending on how long it waits, I might make it till the following Sunday, but I think Thursday's plenty, especially since we don't have anything else. So I will definitely post it tonight, the practice test, but I'm also going to post test 4 as well, which is the actual test. So you'll have a practice test 4 and a test 4 on chapters 21 and 22. They will be posted tonight, and like I said, you'll have at least until Thursday of next week to have it done.
So test 4 is going to be the in-person test, and you said you're going to put up a practice test for that.
I'm going to put up a practice test, but it's going to be it's going to be not an in-person, but a online test.
Okay. And so 4 would be okay. I'm sorry.
Yeah. 4 would be on covering 21 and 22, but of course all our tests are comprehensive, so I could throw some stuff from the previous ones, but it mostly doesn't on that.
All right. Well, a lot of people left the class already, so you might want to make an announcement about that on Canvas.
I will. Don't worry. I will definitely do that. All right.
All right.
Gavin.
Thank you.
Or Taylor, sorry.
Have a good one.
You too. Gavin or John, do you have any questions? Yeah, just put a warning on there just in case they see this, but don't necessarily see my announcement. It looks like everybody's left. I'm going to stop sharing and tell everybody bye-bye. Bye-bye. Nice seeing you.